Hello everyone, good afternoon, welcome back. Okay, so today we're gonna do differentiation. Right. So if you've done add math, which I'm sure most of you have done already, you would recognize most, if not all, of these things. Yep. So in fact, for A2, there are three parts to differentiation. So the first one is very similar to add math, almost identical, you could say. And then the second part is implicit differentiation. And the third part is parametric differentiation. If you've done further math, you've actually done all three. So, yeah, you can just skip this class and jump straight to the past years if you so choose to. But for those who haven't done further math, let's get started. All right, so go to screen share. Okay. Make my pointer bigger. Okay, right. So, previously in AS, you know that when you differentiate some function of x to the power of n, you would get n times the differentiated function times the same function, but then the power is reduced by 1. So, for example, if I differentiate bracket 2x squared plus 3 to the power of 5, I'll bring the power down and I differentiate whatever's inside, which is going to give me 4x. And then I write the same thing here, 2x squared plus 3, and I reduce the power by 1. So it's now power 4. Okay, this one we've done in AS. So the next thing you want to know is, let me just put that, just number it. So the second one is, what happens if you differentiate sine? Or more specifically, sine and then a function of x. Or actually, you want, let's try to do it something different. Let's move this here a little. Let's do it like that. So if you differentiate x to the power of n, you will get nx n minus 1. Okay, I've shown you the proof for this back in AS. So the second one is, if you differentiate sine x, you would actually get cos x. And then the third one is, if you differentiate cos x, you would get negative sine x. And then you also have, if you differentiate the exponential function e to the power of x, you would get the same thing. And then if you differentiate ln x, not log base 10 or log base something else, it has to be log base e, ln. Okay, so if you differentiate ln x, you would get 1 over x. Okay, so these are the basic rules of differentiation, which you can derive using the first principles of differentiation. Remember back in AS, we did something like, if you want to differentiate some function, it actually means taking the limit as h approaches 0 of fx plus h minus fx over x. Remember this? This is differentiation from first principles. You're doing it from scratch. So if you apply these principles to sine, cos, ex, and ln x, you would actually get these values here. So the proof is actually out of the scope of the syllabus, but if you are interested, I can send them to you. I've actually done them on a separate document already, just to give you a very brief look at what it looks like. It's over here. So sine, different derivative of sine. There we go. There. So you differentiate this to get this, and you start by putting the function in here, put that in the differentiation for first principles equation, and then you expand it, and you have to use an identity, this specific identity right here, which is actually how should I explain this? You have to use the addition formula from the last chapter to expand this guy to get this. Okay, it's not immediately obvious why it is, but if you expand, you would actually get this one. So you have to use this identity, you put it in here, and you have to use the small angle approximation, and eventually you will get cos x. And again, this is not in the syllabus, so you don't have to know this. And you can do the same thing for cosine. Again, use a similar identity and you get negative sign. You can also do the same thing for the derivative of the exponential function. Do I have it here? Oh, there we go. This one requires the definition of the Euler's number, which is what I've shown you in chapter 1, right? The Euler's number is actually the small e, 2.718. So you have to use that definition. You expand it, eventually you will get ex. So differentiating ex gives you ex. For the logarithmic function, ln, you have to use Euler's number's definition again, and eventually you get 1/x. Like I said, you don't have to know all this, so I'm not going to go through all that in detail. But suffice to say, these are the 5 things that you can derive from scratch. Okay, everything else, tangent or any other function like cosecant, whatever, all of that can actually be derived using these 5 basic rules. Okay, so, and well, the chain rule. So, what if we replace this x with some function of x? So you would get something like this. And the reason you get this in the first place is using the chain rule, which I'm not gonna go into detail here because again, it's not really necessary to know. You just have to know that this becomes this. Okay, so suppose say you have, I'm gonna differentiate sine and then some function of x. What's going to happen then? Well, you would actually get the differentiated function, and then you differentiate your sine fx. So you get cos fx, like this. Okay, so for example, suppose I differentiate sine, and let's say we put 1 minus 7x cubed to the power, well, I don't want to put any power, so I'll leave it like that. Okay, so what do we get? Well, we are going to get, what happens when you differentiate 1 minus 7x cubed? We get negative 21x squared, right? And then we write the same thing, but now we write it as cos, and we insert the same function. There we go. Similarly, what happens when you differentiate cos fx? Well, you will get f prime x, and then you get negative sine fx. So a quick example, suppose I differentiate cos, let's say x cubed minus x squared. Okay, what am I going to get? Well, first you differentiate whatever's inside the function, which is going to give you 3x squared minus 2x, and then negative sine x cubed minus x squared. Okay, so basically you are just differentiating whatever's inside the function, put it out here, and then you differentiate this part normally, and you treat fx as some function, as the unknown x, essentially, this one and this one. Okay, so you can see here, sine x becomes cos x, sine x becomes cos x. The only difference is you have to differentiate whatever is inside here and put it out here. Okay? Right. Now, let's do another example. What if I were to differentiate sine cubed x? What is this then? Well, sine cubed x is actually not something like that. It's also not something like this, but it is actually this guy in disguise. because sine cubed x is actually d dx sine x to the power of 3. So there is a function of x inside a power, right? See here, function of x inside a power. So to differentiate this, all you got to do is bring the power down, differentiate whatever's inside. So you're differentiating the sine, which means you have to put a cos in there. So this becomes a cos x. And then now you write the same thing and reduce the power by 1. So that's how you differentiate this guy in the first place. Okay. Now, what if I were to differentiate sine cubed 2x? Okay, so sine cubed 2x is actually the same as bracket sine 2x cubed. So again, this is actually a function inside the power, similar to this guy here. It's nothing to do with this, by the way. It's this one actually. This is a very common mistake that people do. You have to follow this one. So sine 2x, you want to put the power down, and now you want to differentiate sine 2x. So what happens when you differentiate sine 2x? Now you have to use this rule here. Okay, because sine 2x, this 2x is actually your function of x. So first we differentiate 2, we get a 2, and then we differentiate sine, we get cos 2x. And now we write the same function, sine 2x, and reduce the power by 1. Okay, so that's how you differentiate this guy here. So this one, you have to use this rule and this rule. Okay. Right then, moving on to the exponential function. So when you differentiate e to the power of fx, you would actually get f prime x, e, and then fx again. So if you have some function of x up here, all you have to do is differentiate it and put it in front like that. For example, suppose I have e to the power of 2x plus x squared. Okay. Well, first we're gonna differentiate whatever is up here in the power. So that's gonna give us 2 plus 2x. And then we write e 2x plus x squared. There. Okay. Next one, we have the ln x. So what happens if we differentiate ln and then some function of x? So based on what we've done so far, you might have noticed a pattern. You see that the differentiated function is always multiplied by the original thingy, right? You see here there's a cos x, this is a cos x, and there's always something in front, and that something in front is always the derivative of the function. You can see here, here, you're always multiplying by f prime x. So when you differentiate ln fx, you get the same thing. You multiply by f prime x, and then you times it with 1 over fx. So you get f prime x over fx. So quick example, let's say we differentiate ln, let's say 2x plus 7x cubed. Okay, so you differentiate 2x plus 7x cubed, which is going to give you x, sorry, not x, it's going to give you 2 plus 21x squared, and then you divide that with 2x plus 7x cubed. There, so you differentiate that, put it up here, and then you write the same thing, put it down here. Done. Okay, there we go. In case you've forgotten how I go from here to here, or here to here, I think I'll just do one, I'll just explain something very quickly. I'll explain the chain rule very, very quickly. We've actually done this in AS, but in case you've forgotten, let me just sort of refresh your memory a bit. So let's say we are trying to differentiate sine some function of x. So maybe this function of x is 2x plus 1. Okay. However, the only rule we know is this rule here. We know that differentiating sine x gives us cos x. But this is not x, this is 2x plus 1. So what can we do? Well, what we can do is we can replace the 2x plus 1 with a u. Okay, so now this is going to be d dx sine u. So sine u is just sine times an unknown, right? Sine with an unknown, right? So you can just differentiate normally. However, the problem here is we're differentiating with respect to x, not with respect to u. So how can you differentiate with respect to u? Well, you have to multiply this guy with du over du. Du over du is just 1. I'm just multiplying by 1. I'm not changing the equation. And I'm going to swap the order of d and du. So I'm going to get du dx here, and then d du sine u. So because when you multiply something, a times b is the same as b times a, so the order doesn't matter. So you can swap these two around. So now we have d du times sine u, which means you're trying to differentiate differentiate sine u with respect to u, and we know what's that going to give us. It's going to give us cos u. Okay, so that's going to give me cos u right here. What about this guy, du dx? Well, du dx is actually from here. You have to differentiate this guy, which gives you 2. So du dx is actually 2. Therefore, we're going to get 2 cos u is actually 2x plus 1. So that is the very short version of the chain rule. Okay, as you can see, if I try to differentiate sine with a function, I have to differentiate this function, put it in front, and then I write the same function, put it at the back, and then I differentiate sine normally. So sine gives me cos. So based on this pattern, we can derive this general formula right here. And that's how you get this equation from this equation. And you can do the same for this one, and this one. Okay, so in any case, I've actually given you guys a summary of all the different kinds of differentiation. It's on Google Classroom. You can just download it. It's all there. Okay, and that's it. Really, that's it for the first part of differentiation. So maybe we can do a quick exercise. I'll do a couple of past years just to give you an idea. Oh wait, actually before that, there's also 2 other things I have to mention. You also need to know how to do the quotient rule and the product rule. So suppose you have 2 functions, fx, gx, and you want to differentiate this composite function right here. What do you do? Well, just to make things a bit simpler, I'm going to say fx is actually u, gx is actually v. And if I differentiate fx, f prime x, I'll call that u prime. If I differentiate gx, I'll call that v prime. So according to the product rule, when you differentiate this guy here, a composite function that's a product of each other, you actually have to go u v prime plus v u prime. Okay, for example, suppose I want to differentiate a e to the power of 2x times sine x. Okay, as you can see, this is a product of 2 functions. So first we're going to write e to x down here, and then we're going to differentiate sine x, which gives us cos x, and then we're going to add that with sine x, and then we differentiate e to x, which gives us 2e to x. And that's how you use the product rule. Right, moving on. The other one is the quotient rule. So suppose you're trying to differentiate fx over gx, a composite function that looks like a quotient. Okay, again, I'm going to call this u, I'm going to call this v, and we're going to use the same notations for f prime x and g prime x, so u prime and v prime. So according to the quotient rule, when we differentiate a quotient, we actually get v u prime minus u v prime over v squared. So the order here is important. You must always start with v, and then you subtract that with u. You can't do u minus v because 1 minus 2 is different to 2 minus 1. The order when it comes to subtraction matters. However, the order for addition doesn't matter. So you can swap this around, it doesn't really change anything. Okay, for example, let's say they want you to differentiate tangent x. Wait a minute, we haven't done tangent x, right? Actually, we have. Tangent x is actually sine over cos. So we are trying to differentiate sine x over cos x. And as you can see, this is a quotient. So whenever you get a function that is not one of the 5 basic functions, all you have to do is write it in the form such that it is one of the 5 basic functions, and then you can use the 5 basic rules to differentiate. Any kind of function works the same, okay? Anyway, so you can see this is a quotient. So first off, we're going to start by writing cos x, and then differentiate sin x, which gives me cos x again. And then, hang on, I'm running out of space. And then I'm going to write sin x here and differentiate cos x, which gives me negative sin x, and I'm going to divide that with cos squared x. So I'm going to get cos squared x plus sine squared x over cos squared x, which is actually 1 over cos squared x, which is actually secant squared x. There we go. So this is not a basic it's not one of the basic rules of differentiation, but it is one of the more commonly seen functions in A levels. So it's actually very useful to know that differentiating tangent gives me secant squared. So despite it not being one of the basic rules of differentiation, I would highly recommend that you remember this particular equation, because it's going to save you a lot of time in the exam instead of having to do this every time you see tangent x. Okay, there we go. So product rule, quotient rule, the 5 basic rules over here. That's all you have to know for the first part of differentiation. And then there's also the usual finding the stationary point, you differentiate, equate it to 0. Finding the nature of the stationary point, differentiate twice. If it's more than 0, minimum point. If it's less than 0, it's a maximum point. But that one you've done in AS already, so I don't think I have to repeat myself. Okay, so let's do some past years. So after doing this past year question, I'll let you guys carry on with some of the exercises in the textbook, or if you are feeling up for it, you could immediately jump to the past years, and you probably can, because this is just add math, really. This is more of a refresher course than anything. We haven't actually done anything new to you yet, especially if you have done add math. And I think all of you have done add math, if I'm not mistaken. Anyway, after this, I'm going to discuss the mock exam papers. So for those of you who did not take the mock exam papers, feel free to go off and do your own thing after that. For those of you who have, just stick around and we'll go through some of the questions. Okay, so let's do this part here. You have a curve with some equation that's given. Find the x-coordinate of the stationary point of the curve in the interval here. Give answers correct to 3 decimal place. So they want you to find the stationary point. Stationary point means dy dx equals to 0, right? The gradient of the stationary point is always 0. So first we have to differentiate this guy here. As you can see, this is a quotient because you have something divided by something. So we're going to start by writing tangent 1 over 2x. And then we differentiate e3x. So differentiating e3x is going to give me 3e3x. And then minus e3x. And then now we have to differentiate tangent. So we know that when we differentiate tangent, we actually get secant squared x. However, what happens if we differentiate tangent with some function of x? So based on the 5 rules of differentiation that I've shown you earlier, the pattern seems to suggest that you would actually get the derivative of the function and then times that with secant squared and then the function. And that is exactly what's going to happen. You can prove this for yourself using the chain rule, but I'm not going to do that here. So you would actually get 1/2 and then secant squared 1/2x. And then you're going to divide by the denominator squared, which is tangent squared 1/2x. There we go. And then we have to equate this to 0 because it is, we're trying to find the stationary point. That equals to 0. Okay, so we're going to multiply the denominator up here, so that disappears, which means we are left with 3 tangent half x e3x. And then we're going to move this guy to the right, which gives us e3x. Half right there, secant squared 1/2x. Okay. So, oh wait, actually, what we should have done is we should have done like this. Hang on, put here 0, and then minus half e3x secant squared half x. So a common mistake that people tend to make here is you just divide everything by e3x to get rid of this. However, if you have a choice between dividing everything by e3x or factorizing e3x, you should always factorize, because if you divide, you might lose out a potential solution. Okay, so you want to factorize e3x, which gives you 3 tangent half x minus half secant squared half x. So now we have some number times some number equals to 0, which means one of those numbers must be 0. So e3x equals 0, or 3 tangent half x minus half secant squared half x equals 0. However, this is impossible. You can't raise e to some power and get 0. Therefore, we can just ignore this one. So at this point, you might be wondering, well, since we're going to ignore this anyway, why not just divide everything by e3x and be done with that? Well, the thing is, sometimes you may not have e3x here. You might have a different function, maybe x plus 1 or something like that, which would give you another potential solution. So you should never just divide everything by something. You should always factorize if you can, okay? Anyway, coming back to this guy here, we're gonna... okay, so if you look at this, you can see we have tangent and we have secant squared, but they are not the same function. And you can't really do anything with this unless you convert one of these things to just one of the trigo functions. So there's actually an identity that we can use here, because you can see this is power 1, this is power of 2, which seems to imply that this might be a quadratic equation in disguise. So which identity should we use? We can actually use the basic identity here. We divide everything by, let's say, cos squared x, which is going to give us tangent squared x. Dividing by cos squared x is 1. This is secant squared x. So as you can see, secant squared x is actually tangent squared plus 1. So I'm going to put that in here. Expand and simplify. And I get rid of the negative, actually. Okay, so now you can see here we have half u squared minus 3u plus half, which is actually a quadratic. Multiplying everything by 2, we get u squared minus 6u plus 1. And then we factorize this guy here. Oh, seems like we can't factorize this nicely, so we have to use the quadratic formula. So u is equals to, let's see, negative b plus minus b squared minus 4ac, so minus 4 over 2a. So 6 plus minus 32 over 2. So we can actually take out 2 out, so that's 8 in there. So that's going to be 3 plus minus square root of 8, which is actually square root of 2 and 2. Okay, so u is actually tangent half x, and then you just solve this and you get your answer. Okay, there we go. Okay, right. So you can actually try some of these questions here in the textbook. You want to start with something less difficult. Let me see. Start with 4a. (4b) and I think 4c. 4c is for trigo functions. 4c, yeah. So you can try 4a, b, and c. 4a, b, and c. You can try all these questions here. So those of you without a textbook, I'll send you the exercises later after the class. Okay, so we are done for now. Let's take a 5-minute break, and then we will discuss the mock exam papers. Well, we're not going to discuss all of it, but I've gotten some questions from some of you, so we'll discuss those specific questions. If you have anything else that you want to add to the list of questions, feel free to send them to me. Okay? All right. So for those of you who are not who were not taking the mock exam, you can leave now and try 4a, b, and c or the past years. All right. I'll see you guys in 5 minutes, and those of you who are not taking the mock exam, I'll see you tomorrow. All right. Latest. Be right back. Okay, you guys ready? Let me get rid of this. So far, I've only gotten questions for paper 1. Nothing for statistics, which is admittedly a bit strange, but okay, whatever. Let's go through questions 1. What was it? 1. Hang on, let me just check again. Come on, phone. Question 13, 8, and 10. Okay. I'm going to go through question 13, 8, and 10. Oh, wait. Wait a minute. Where did I put it again? Yep, okay, found it. Question 13, 8, and 10. Okay, so you have a water container, like an inverted pyramid, blah, blah, blah. Surface of the water is a square with side half h, so half h here, half h there. Find the volume of the water in the container in terms of h. Okay. So the volume of the pyramid having a base area A and vertical height is this. So they've actually given you the equation already. So the volume is just 1/3 times the area. The area is actually half h times half h. And then the height is just height, h. So simplifying this, you get 1/4, 1/12, h cubed, and done. Okay, and then the second part of the question. Water is steadily dripping into the container at some constant rate. So this is actually dv dt is 20, right? Because you can see here the unit is in centimeters cube. So that's volume, right? So dv and then over time, because it says per minute, minute is time, a measurement of time. Hey, Shavi Jane, hello, hello. Find the rate in cm per minute at which the water level is rising when the height of the water level is 10. So they want you to find the rate. Rate means you have to divide by time. And it says they want to find how fast the water level is rising. So that is your height. So this is actually asking you for the rate of change of height, dh dt. So in order to find dh dt, you have to do dh over dv times dv over dt. If you don't know how I got this in the first place, imagine multiplying this by 1. Okay, so when you multiply by 1, you can, instead of writing 1, you can write it as dv over dv. Why do I use dv? Because previously we were given dv over dt, which kind of hints that we are supposed to use v somewhere. So now we're going to swap the bottom two. We're going to swap this guy here with this guy here. Just going to swap them around. And that's going to give me dh dv times dv dt. Okay, so I haven't actually changed anything because I'm just multiplying by 1. So dh dv, we don't know what that is, but we can actually work that out because you can see we have v in terms of h. We know that v is equals to 1 over 12 h cubed. So dv dh is actually 1 over 4 h squared, which is actually h squared over 4. Therefore, dv, hang on, therefore dh dv is going to be 4 over h squared because I'm just flipping it upside down. So putting that in here, we get 4 over h squared. dv dt is given by the question to be 20. So we get 80 over h squared. And you can see here that they want you to find the rate when the water level is 10. Water level refers to the height. Therefore, you can just put this in as 80 over 100. Therefore, you get 0.8. And done. Okay, so that's how you do question 8. Let's move on to question, what was it again? Question 10. Okay. Let's look at question 10. Okay, so the graphs intersect at points A and B, and the graphs given are y equals cos x, which is this line here, and then tangent x, which is these two lines. Find by calculation the x coordinate of A. So how do you find the points of interception? You equate the two equations together. So tangent x equals cosine x. Tangent x is sine over cos. Move the cos over, we get cos squared x. Using the identity, we get 1 minus sine squared x. Rearranging, we get a quadratic. Right, you can see this is like a u squared plus u minus 1. So solving this quadratic, you can't actually solve normally because it doesn't factorize out nicely into integer solutions. So we have to use the quadratic formula, which is negative b plus minus b squared minus 4ac over 2a. So that's going to give us sine x equals to negative 1 plus minus 5 over 2. You should study this for your 12th grade math. Find it hard, but managed it. Yeah, in fact, I think this is one of the more fun chapters. Even when I was back in my schooling days, I also really enjoyed doing integration and differentiation, though I didn't really know why exactly they work the way they do. But yeah, so what do we have here? We actually have two answers. So the first one is negative 1 plus root 5 divided by 2. We get 0.618, and then the other answer is negative 1 minus root 5 over 2, which is negative 1.618. So these numbers are actually quite significant because they are actually numbers associated with the golden ratio. But that's not in the syllabus, but I just thought I'd point it out because it reminded me of that. Anyway, you still remember all the formulas? Wow, nice. Okay, so sine x. You can see here that our domain is from 0 to pi, right? X is between 0 and pi. So we're only interested in the first quadrant. So x is going to be equals to arcsine of 0.618, which is actually 38.2 degrees. And then arcsine of 1.618, just take the principal value, but this is actually greater than 1. You can't have sine with range greater than 1. So we ignore this one. Okay, and then what else is there? That's it. Yeah, technically, when you work out the arcsine of 0.618, you should get two answers because it's in the first and second quadrant. Actually, I just realized something. The domain is from 0 to pi, which means you are looking at the first two quadrants, so I messed up there. So the next, the other answer should actually be 180 minus 38.2, which is 141.8 degrees. But we actually ignore this one, the second one. So the answer should be x is equals to 38.2 degrees. Change that to radians. 38.2 times pi divided by 180 gives me 0.667 radians. Okay, because the second x coordinate refers to b, the x coordinate for b. Okay, next up, let's look at the next part of the question here. What do we have? Find by calculation the coordinates of b. Okay, well, we actually already know what the x coordinate is because we worked it out earlier. It's actually this one here. So the x coordinate of b is going to be 141.8 degrees, but I'm going to have to change that to radians. So multiply by pi divided by 180 gives us 2.47. Okay, so now that we have worked out the x coordinate, how do we find the y coordinate? Well, we can actually put in the x coordinate into either of these functions, and that's going to give us our y coordinate. So let's say we're going to put it into y equals tangent x, so tangent 2.47. Change the calculator to radian mode. Tangent of that gives me negative 0.787, and therefore your answer is 2.47, negative 0.87, and done. There we go. Okay. Moving on to the last question. I think that's question 13. This one. Okay, let me just move this over here. Okay, so you're given the equation of the curve, and then you want to find the volume obtained when the region bounded by the curve, the x-axis, is in a line rotated 360 about the x-axis. Okay, so remember when you want to rotate something around the x-axis, you have to integrate the function, and then you square the function. You multiply it by pi, and then you do dx. And you have to put the limits that you're interested in, which is, well, in this case, 1 to 2. Okay, whenever you see the word volume and then rotation, this is what you want to do. So, what is our function? Our function is 4 over 2x minus 1. So when you square this, you will get 16 over 2x minus 1 squared dx. Okay, and I can actually rewrite this as 16 times 2x minus 1 to the power of minus 2. I can take out the 16. Oops, hang on. So remember, whenever you try to integrate some function to some power, and if the function is linear, you can actually get, you would actually get fx and then n plus 1 over n plus 1, and then the derivative of the function down here, plus c. Okay, so this fulfills those conditions that we need. So we can just write that as 2x minus 1 to the power of minus 1 over minus 1. You differentiate whatever's inside, it's going to give us 2. And then the limit is from 1 to 2. So we're going to simplify this guy here. We get negative 2. Put it out here. We got negative 32 pi. And then 2x minus 1. 1, 2. Okay, so we're going to get 1 over 4 minus 1, which is 3, minus 1 over 1. So that's going to give us negative 2 over 3, which is 32 pi times 2 over 3, which is 64 divided by 3. What do we get? 64 divided by 3. We just leave it at 64 over 3, I suppose. 64 over 3 pi. Yep. And there it is. Finished. Okay, moving on to the next part of the question. Given that the line is normal to the curve, this is a normal line to the curve, find the possible values of the constant c. All right, so this curve is actually 1 over fx. So the curve kind of looks like something like this. So this other line is a normal line to the curve. Okay. Let me think. Given that the line is a normal line to the curve. Find the possible values of the constant c. Seems like it's missing something. Shouldn't it tell you that it's a normal line to the curve at a given point? That's kind of strange. Wait a minute. How come we got a different answer? 16 pi over 3. Did I mess something up? Hang on, let me just check. Differentiate this, we get 2, put it 1 here. Oh, whoops, sorry. This should have been an 8. Because I should be dividing, not multiplying. 8. 8. Okay, this should be an 8 right here, so 8 right there. So 16 over 3. Okay, that's fine. What about this one? Strange. Let me just check something. This is May, June 15. Paper 1, 2. Question 13. What? There is no question 13. Oh, okay. I thought it was missing something, but apparently not. It is a normal line to the curve. Find the Oh, okay, I know what it means. So this is actually a curve. So you can have a line like this. But then if you draw a line like that, it's going to intersect the curve again at some point, right? Because this curve stretches indefinitely in both directions, which means it is not going to be a tangent. No, sorry, a normal. So a normal, wait, actually no. A normal, hang on, I was thinking of something else. Tangent means it intersects at one point. Normal means it should be perpendicular. But this is a curve, it's not a line. So how can it be perpendicular when the gradient is not constant? Now this is very weird. Let me think. Given that the line is a normal line to the curve, find the possible values of the constant c. It is a normal line to the curve, but the curve doesn't have a fixed gradient. What do they mean by this? Unless I'm imagining the curve wrong, but I'm quite sure it looks like a 1/x graph. Let me just double check. So the curve is 4/2x minus 1. Yeah, it looks like this. Strange. Given that the line is a normal line to the curve, find the possible values of the constant c. A normal line to the curve. Oh, I think what they mean is, because you can only draw one possible tangent. Well, actually, you have multiple ways of drawing a tangent. You could draw a tangent here, you could draw a tangent here, or even here. So there are so many different, infinitely many different ways of drawing a tangent. So there shouldn't be a unique normal line. What? Let's see what they do with the answer. So they're taking m equals to half m of the tangent equals to minus 2. That is kind of weird. Unless there's a definition of the normal line that I'm not familiar with. Hang on. Normal line. Normal straight line which is perpendicular to the tangent. Yeah, but we don't have the equation of the tangent. Okay, suppose we want to find the equation of the tangent. What we'll do is we'll differentiate the function, right? We're going to differentiate the function, which is going to give us d dx, and we put a 4 up there. And then this is actually 2x minus 1 to the power minus 1. So when you differentiate this guy, you would get minus 1 here. Differentiate whatever's inside, you get a 2, and then you reduce the power by 1. So you end up with negative 8 over 2x minus 1 squared. So depending on which value of x that you've chosen, you would have a different gradient for the function. Okay, suppose we leave it as unknowns, and then to find the gradient of the normal, we have to multiply that with the gradient of the tangent and equate that to -1. So the gradient of your normal must be 2x minus 1 squared over 8. All right. And the question tells you that the equation of the normal is 2y equals to x plus c. If we rearrange this, we're going to get y is equals to half x plus c over 2, which implies that the gradient of the normal must be a half. Okay, I see what's going on. So we're supposed to equate these two things together, and so we get 2x minus 1 squared of 8 equals to a half, which is actually 2x minus 1 squared equals to 4, which means 2x minus 1 equals to plus minus 2, so x must be equals to either 3 over 2 or x is equals to minus 1 over 2. Okay, so if x is 3 over 2, then the y coordinate, we can actually put that into our equation, which was y equals to 4 over 2x minus 1 squared, right? So if x is 3 over 2, we are going to get 3 minus 1 squared, which is 1. So y will be 1. If x is a half, we are going to get 4 and then negative 1 minus 1 squared, which again is 1. There we go. So we have two possible coordinates. So now we can use these two possible coordinates to find our two possible values of c by substituting these guys into this guy. Well, that is quite a bizarre question. So we're going to take this guy, chuck that into this guy to find c. So c1 is going to be equals to, let's see, 2y minus x. So 2y is 2 minus x is 3 over 2, so we get a half. Or c2 is going to be 2 minus plus a half, which is 5 over 2. So we get a half or 5 over 2. Wait a minute, why is this negative 7 over 2? Did I mess up again? 2 minus 3 over 2 is half. No, it's correct. What? Let's say this is 2, 3 divided by 2 is 3 over 2. Did I mess up something? X is 3 over 2 or negative a half, yep. And then, oh, I think I messed up my y. This guy is 2x minus 1. So if I put 3 over 2 in here, I should get 3 minus 1, which is 2, so 2 squared is 4. Wait a minute. 3 over 2, put it in here. Did I write the right one? Oh, it's not squared. Oops. This is not squared. Not squared over here. Which means this should be 2. Okay. This should be minus 2. So this guy is minus 2, this guy is 2. Which means this guy would be 4 minus 3 over 2, which is 5 over 2. Yep. And then this guy is 4 plus 1 over 2, which is 7 over 2. There we go. Hey, Filipina. Listen to Brazilian funk? Sure. You can share a link if you want. I'll leave it to the discretion of the viewers to see whether they want to click on it. Okay, so there we go. I think that's the only 3 questions that you guys have sent me. Is there anything else that you guys want me to go through? Anything at all? Yes? No? Maybe? All right. In that case, we shall stop here for today. And I will see you guys tomorrow for more math. Okie dokie. Goodbye. See ya.